All right, 2.3, Similarity Returns. Before we get into this problem, I found that this curriculum sort of glanced over something that's pretty important. It may seem obvious when I explain it, but there's no reason you would just know this, you would just assume it. You have to explain it. So let's say we have, here we've got a circle, let's call it circle C, since the name of the center is vertex C. Okay, so we've got a central angle here, angle ACB. And that subtends arc AB. We also have let's call this D. We also have an inscribed angle here, ADB. So angle ADB also subtends arc AB. And what the textbook didn't really talk about was, let's say the measure of this angle is x degrees. If we say a central angle is x degrees, then the arc it subtends is also that same degree measurement. So we could say that the measure of arc AB is equal to x degrees. And that sort of makes sense if you think about it. Let's say this was a right angle, right? It was 90 degrees. It's like we're taking up a quarter of the circle, sort of 90, right? Well, if I think of an entire circle as 360, I'm also taking up a quarter of that circle's circumference. So this arc is always going to be equal in measure to whatever the central angle that subtends it is. I mean, that's something I really don't feel like they went over at all in that first lesson. So, let's say I didn't even know this central angle, right? Let's say I completely didn't tell me that in the problem. Well, since I know that the central, if this arc has a measure of x degrees, that must mean the central angle associated with that arc, or that subtends that arc, must also be x degrees. So therefore I know if this is x degrees, I can also say this inscribed angle is x over 2 degrees based on what we know about inscribed angles. So really what I'm trying to say here is, technically we don't need a central angle. If I know the measure of the arc that's being subtended by that inscribed angle, I can also find out its measurement. If this was 90, this would be 45. So in this problem you're about to see, they're not going to give us a central angle, right? This vertex F doesn't even look like it's anywhere near the center, and they don't tell us that F is the center, so I couldn't assume this was a central angle. So we're going to have to make some inferences, not inferences, but we're going to have to solve this problem knowing about the relationship between the arc and the inscribed angle that subtends it. We're not going to be talking about central angles at all in this problem. Okay, so hopefully that makes sense, that these two angles here are always going to be the same measure, the arc and the angle, I'm sorry. So yeah, we'll see how that is going to play out here. So 2.3, Similarity Returns. The image shows a circle with chords CD, CB, ED, and EB. The highlighted arc from point C to point E measures 100 degrees. The highlighted arc from point D to point B measures 140 degrees. Prove that the triangles CFD and EFB are similar. So they're talking about these triangles here. We want to prove they're similar. All right, we've seen diagrams like this many times throughout the year. Not with a circle, but sort of this diagram where you got these two triangles paired off that way. So the first thing I'm going to do is label whatever they've told me the measurement of. So they told me that the arc from C to E measures 100 degrees. So I can say the measure of arc CE, sorry, not CB. The measure of arc CE is equal to 100 degrees. The arc from point D to point B, or just arc DB, is 140 degrees. Measure of DB. All right, and these are both minor arcs because they're less than 180 degrees, right? The major arc would be much greater. It would be 260, and then it would be 220. Okay, so why is this important? Well, if I know the measure of an arc, I can also find the measure of a central angle, which unfortunately we don't have here. And what we just talked about, I can also find the measure of any inscribed angle that subtends that arc. So, if this measure is 140 degrees, are there any inscribed angles in this diagram that subtend this arc? All right, I'm going to highlight those. So anytime you're looking to find inscribed angles that subtend a particular arc, you're going to want to look at the endpoints of the arc. So I'm looking at D, I'm looking at B, and I'm seeing, do I see any angles that hit those 2 points? Well, actually, I do, and there's multiple. I can see this angle right here, so I highlight in purple, is going to subtend that arc, right? DCB. So the measure of angle DCB is going to be equal to half of 140, or just 70 degrees. All right, so I know this angle here is 70. I can also see that there's another arc, another inscribed angle that subtends that arc. Angle DEB, right? If the two endpoints right here are the first and last letter of the angle name, then I know it subtends it. All right, DEB, right? It's like it's hugging that arc in a way, intercepting it. All right, so this will also be 70 degrees. Now, you might have already noticed at this point that there's a pair of angles that are congruent here that I haven't marked up. And you'd be right. One of our favorite reasons in a proof, vertical angles right here. These two angles have to be congruent. I don't know their measure per se, but I do know that they are congruent. So already I've proven that these two triangles are similar by a similarity. The textbook goes ahead and gives us some additional information, which technically we don't need, but I'll go ahead and show it to you anyways. They tell us that the measure of arc CE is 100 degrees. So I can also find another pair of inscribed angles that subtend that arc. All right, this green angle here, angle CDE, subtends arc CE. So that's 100. This angle here is going to be 50 degrees. And I can do the same thing with CBE. It is subtending this arc, so it must be half of its measure, 50 degrees. I guess the only benefit to knowing this is I now can say, well, that's 70 and that's 50. 50 plus 70 is 120, and then 180 minus 120 is 60. So I can say that both these angles here are 60, but I don't really need to know the exact measurement to know that the triangles are congruent. I just need to know that they have at least two pairs of congruent angles, corresponding congruent angles. So let's see if that actually matches up. C and E are both 70. F and F obviously are going to be the same measure of 60-60. And D and B are 50-50, so they do have the corresponding parts. So we're going to say that triangle CFD is similar to the triangle EFB by angle similarity. As it happens, there are actually a lot of very important mathematical relationships that stem from this diagram. And I'm going to just draw it again just because I think there's a lot going on there and I don't want to confuse anyone too much. Get this out of the way. Yes, I do have multiple compasses in my house. Not proud of it. All right, so let's draw that diagram again. So I mean, I see why it was helpful that they gave us the actual measurements, but really I think it's more interesting to prove something when you use variables, because then it shows it works for every case. So we can see that very much in the same vein. These two angles, let me use a pointer. Right, these two angles, just like these two, subtend the same mark. So they're going to be the same measure of x. All right, and we can do the same thing. You know, these are going to be the same because they're vertical. And these both subtend this arc up here, y. Okay, so what I'm going to do is I'm going to, let's see, label these sides. A, B, C, D, E. Okay. And what we really want to talk about now is more than just the angles being congruent. When we talk about similar triangles, we also talk about, you know, certain sides being proportional. So if I'm looking at this side BC here, right, I see BC is opposite angle y. So when I make a proportion, I'm going to want to pick the angle opposite angle y in the other triangle. So opposite angle y in this triangle, we have CD. Okay. So now I started off in the numerator with a side in this first triangle here. So I'm going to start off with another side in the same triangle. I'm going to choose CA. All right, AKA, I'm sorry, not AKA, but CA was opposite angle X. So now if I look opposite angle X here, that'll be side CE. So really what I'm trying to drive home here is that, let's say we've got segments, right? BC, I'm just going to call 1, CD, let's call 2, CA, let's call 3, and CE, let's call 4. What we always know is going to be true is that if I make a proportion with these sides, 1 over 2 equals 3 over 4. All right, and these are just labels. They're not the actual measure. I don't know if that's 1 centimeter or what it is. We can create you know, equivalent proportions. When I cross multiply, I get 1 times 4 equals 2 times 3. Again, I'm not talking about the actual numbers 1, 4, 2, and 3. I'm talking about how I've labeled it. Really what this is saying is that when you have two chords that intersect in a circle, if you multiply like the lengths of the two parts that were broken up, they're always going to be equal to the other two lengths that you broke up when you multiply them. So that's something that this textbook doesn't cover, and it is something covered on the region. So if you do choose to take that, I want to make sure that you've at least seen this before, and you're not like, oh my God, I've never seen that before. All right, and it all comes from, you know, the similarity proof. So really, if you can prove something is similar, you know, this follows that logic. All right, have a great day.